Hello, welcome back to our section on optimization. I'm sorry I won't be able to be in class today, so I'm going to leave this video. So let me first of all hide this. Okay, so we're going to have a fun little problem here where our friend Kevin wishes to keep a pet pig. All right, you can see in this problem, example 1, PTOP, People for the Ethical Treatment of Pigs, require a minimum of 144 square feet of area to keep a pig. What rectangular dimensions would minimize the length of fence that Kevin needs to create a pig pen? All right, so as we look at this problem, we have to fill in our table. Okay, so verbally, this is really easy. We need to, you can see the words in here. We need to minimize, let me switch to my pen. We need to minimize the length of fencing, okay? I'm gonna call that the perimeter. Okay, so we need to minimize the perimeter. Okay, and our constraints are that we must have the area must be 144 feet squared. Okay, now we need to convert those things into algebraic expressions. Well, to do that, we probably first want to draw a picture. Okay, so let's assume Kevin has a nice little rectangular yard here for his pig. And let's use reasonable variable names like X and Y. Okay, so if we have those names, the perimeter is simply going to be twice X plus twice Y. This side will also be X, and that will be Y. Okay, and the area is X times Y. We know that X times Y must be 144. Okay, so now we should be able to solve this problem using calculus. So we need to minimize P. But right now, P is in terms of two variables, as we saw yesterday. So we have an X and a Y, and we need to get down to one variable. So let's first just start by writing P equals 2X plus 2Y. But we can use, I'm going to sort of indent here, X, Y is 144. So let's eliminate Y. We're going to substitute for it. It's 144 over X. So what is the perimeter? The perimeter can be expressed in terms of X as 2X plus 288 divided by X, or if I want, I can do X to the negative 1. That'd be easier for taking a derivative. 288 divided by X, or 288 X to the negative 1. So now if I want to optimize, either maximize or minimize P, I want to take a derivative and find critical points. So dP dx will be 2 minus 288 X to the negative 2, but I could just quickly write that like that. Okay, so to find the critical points, I'll set this equal to 0. Well, first let's rationalize it. I'm sorry. So let's do a little bit of algebra to make our lives easier. So if we want to rationalize this, X squared is the least common denominator. So 2X squared minus 288 is dP dx. All right. And now let me go up a column. Where will we have critical points? We'll have critical points if X equals 0. All right, or 2X squared 2X squared minus 288 is equal to 0. Now, we don't need to pursue this because you don't have a rectangle if X is 0, so that clearly minimizes, if X is 0, Y will have to be infinite in order to get our area, so it'd be meaningless to have an X equal to 0. So let's just consider what happens when, for the other option. Okay, so that means that 2X squared is equal to 288. So X squared is equal to 144. Oh, wow, you might think Mr. Owen had rigged the numbers. He did. So what is X? X is going to be 12. All right. Now, once again, we need to prove that that is a minimum. So let's do a derivative test of this. I don't want to do a second derivative test because the first derivative is a little bit messy. So I think it's easier to go ahead and just do a first derivative test. I'll have x equals 12. X can't be below 0, so let me put x equals 0 down here. We can't go below that. X could be very, very large. We don't know how big it could get. But let's test this at a point that's way below 12. Let's just do down here like at x equals 1. And if you look at that, you can see dp dx is clearly, the numerator is negative when we evaluate that at 1. And if we do this at a number bigger than 12, let's take a reasonable number like x equals 20. If you put 20 into dp dx, you will get a positive value for that numerator, and the denominator is always negative. Therefore, this is a minimum. Okay, so we do have a minimum at x equals 12, and given that that's the only minimum, it would be the absolute minimum. So x equals 12 works very nicely. We just proved that. And now we can figure out what y is. Well, y was equal to 144 over x. So that's 144 divided by 12, which is also 12. So the dimensions are a square. We want a 12-foot by 12-foot pen. So a square would require the least amount of fence. So if Kevin just has a big open field to build this in, making a 12 by 12 pen will satisfy the conditions of this problem most easily and minimize the amount of fence that he needs to get. Okay, let's continue. Let's do a variation of this. So if Kevin can build the fence beside the house, let's just put a blue line here for the house. And then let's build the fence. It only needs to have 3 sides. He needs to have a side out here and a side over here and a side there. So if we stick with our X and Y, you can put the house on the vertical side, it doesn't matter. We'll end up with the dimensions being the same either way. So using that picture, once again, what is it that we need to do? We need to minimize the length or perimeter, minimize. I'll use length this time, since it's not a full perimeter. It's kind of like the perimeter. And our constraints are, once again, that x, oh, I'm sorry, you're not ready for the equation yet, but the area must be 144. Okay, so looking at that, what is the length? This time the length is going to be x plus 2y. Okay, so you get one of the x sides for free this time. We don't need to put in 2 lengths of x, we just need to put in 1. All right, and the area once again is that xy is 144. Okay, that feet squared. So we can put that in as our little algebraic expression there. And this time let's write L equals x plus 2y. And from what we had before, we know that y is 144 over x, so we can eliminate y using our constraint. So L is equal to x plus 288. I'll do x to the negative 1 again. And then dl dx. We need to find the rate of change to determine where the critical points are. It's simply going to be 1 plus, if you take the derivative, I'm sorry, it's going to be minus 1 minus 288 x to the negative 2, which would be that. Okay, if we get a least common denominator, that would give me x squared minus 288 over x squared. All right, and then to find the critical points, we'll do what we did before. Critical points, or numbers if you wish, okay, are going to happen when x squared equals 0, but we don't really need to worry about that. Obviously, x being 0 isn't helpful, so let's just worry about the numerator. So that's where x squared minus 288 is equal to 0. And therefore, x squared is 288. And we don't need to worry about the negative root because you're not going to make a negative length of fence. So let me just very quickly, calculator, determine that. Okay, so the square root of 288 is 16.97. Okay, so notice x is bigger than it was before, all right? And it's because one of the sides, one of the x sides comes for free, all right? So by making the x a little bit bigger, this will work out more nicely. We need to verify that that is, in fact, a minimum. So let's make a little sign chart. Here's x equals 16.97. We know we can't go below 0. So once again, let's figure out what happens if x were 1. Nice small number, less between 0 and 16.97. Clearly, the numerator of dl dx is negative. So let me write dl dx here. It'll be negative at x equals 1. And if we go up to a number, let's just go up to something like 30. When you square that, you get 900. 900 minus 288 is clearly going to be positive. All right. So we do, in fact, again, have a local minimum. So we just verified that we do have a minimum there. Now we can find the y value. So we just have to determine y is 144 divided by 16.97. Let me just very quickly put that into my calculator. All right, and it looks like we have 8.49. Okay, so that turns out to be that's our y value. So the dimensions will be 16.97 feet by 8.49 feet. Okay, so this is no longer a square. This is a rectangle. And the nice thing is, notice we have more on the x side. And why is that the case? Logically, this side is free. We don't need to buy any fence for that side. So we would rather have a longer x because one of the x sides is free. So that pushes the calculation to favor the x direction rather than the y direction. So we'd have a more rectangular pen for Kevin's pig. Okay, let's move on to one more example based on the same problem. Kevin wishes to keep 2 pigs in adjacent pens. Each pen must have 144 square feet of space to keep P-top happy. The exterior fencing costs $20 per foot, but the interior fence only costs $10 per foot, since it does not need to be as strong. What dimensions minimize Kevin's cost? Okay, so this time we're not against a house. These are out here in a field somewhere. Okay, let me put a dividing fence in a kind of dash line here. Okay, that fence doesn't need to be as strong because if we have pig 1 here, there's my pig. Okay, and pig 2, I guess they have 4 legs, not 2. Okay, there's pig number 2. If pig 1 and 2 hop this fence, they're not running away. Okay, so you can have a smaller fence there than we have on the other side. Okay, so we can label these. Let's just be clear in our labeling. This from there to there is x, and from here to here is y. Okay, so what are we going to do? We're going to minimize the length of fence. Oh, actually, we're going to minimize the cost of the fence. Okay, and then we're going to, because it says right here, let us minimize Kevin's costs. And so we're going to minimize the cost of the fence. Okay, and then we know that, the total area is 288 square feet. Okay, we'll assume it's evenly divided. Obviously, the middle fence can be placed anywhere along there, but we're going to try to keep both pigs happy. So we'll put it right down the middle. So what is the cost? We need a cost equation. All right, well, it looks like we have at $20 per foot. Looks like we have 2 lengths of X. Whoops, so let me change that. That'll be 2 X's, 2 lengths of X on the outside, and 3 lengths, 2 lengths of Y, 2 lengths of Y at $20 per foot. Okay, so 2X plus 2Y is the total length of fence around the outside, and we're going to multiply that by $20 per foot. Okay, but then we need to add on plus 10Y. Okay, the middle fence right here is Y, so we need to add on 1 extra length of Y to subdivide the yard. Okay, but that's only going to cost $10 per foot. So we get 10Y for the cost of that. Okay, so we're adding, we have the 4 outsides, we have 2 X's, 2 Y's, but then on the inside, we have a single length of Y to add up, right? And we know, looking at this, that the total area, that would be X times Y, is now 288 square feet. Okay, so let's do the problem. We know that the cost is what we're trying to minimize, so simply copy this out. I'll distribute a while. So we end up with 40X plus 50Y as the total cost. Okay, now we can kind of do what we did before. Our constraints tell us that Y is going to be 288 over X. Therefore, we can rewrite the cost equation as 40X plus, let's see, we have 50 times 288. I better grab my calculator for that, just to make sure I get it right. 50 times 288, 14,400 over X. Now we're ready to take the derivative of that. dc dx is going to be 40. And then we'll, like before, we'll have minus 14,400 over X squared. So think of that as the second term in the cost equation, 14,400 X to the negative 1. And that explains why we get that as our derivative. Now let's write it in a rational form with a lowest common denominator of X squared. And we have 40X squared minus 14,400 is equal to dc dx. If we want to find the critical points, X squared could be 0, but we're not going to worry about that. So we want 0 to equal 40X squared minus 14,400. So 40X squared is equal to 14,400. We quickly divide that by 40, calculator. So X squared is 360. Let me raise that to the half power. And it looks like X should equal 18.97 feet. Okay, so that's my X value. We need to verify once again that that in fact is a minimum. So doing a first derivative test, we're trying to minimize the cost. We want to make sure we're not accidentally maximizing it. So you have that right there. We can't go below 0, so I'll put an endpoint there. This could go up forever. And we can look at this. And once again, let's put in just a little number like 1. And when you look at that expression for dc dx, we were to put in 40 times 1 squared minus 14,400 is clearly negative. And if we put in a larger number like X equals 20, when you square 20, you have 400. You multiply that by 40, and you're clearly bigger than 14,400. You can double check if you wish, but that will be positive. And therefore, since the first derivative goes from negative to positive, the function was decreasing then increasing, and this in fact is a minimum. We just verified that. Okay, and so now we can determine our y value to get the dimensions. So y is 288 over 18.97. Okay, so my calculator, 288 divided by the answer gives me 15.17 feet. Okay, so what are the dimensions? The total outside of the rectangle have dimensions for the picture that I drew that were 18.97 feet by 15.17 feet. Okay, now let's consider why this answer is what it is. We get more in the x than the y. There's a reason for that. Look at the picture. We need to have 2 lengths in the x direction, but we need to have 3 lengths in the y direction. So we would like to have a little bit more x than y because we're going to need to have more lengths of y. So they raise the cost in the y direction faster than the cost in the x direction. Okay, so that should help you to do the next set of homework problems. I hope that this video was useful.